Hi everyone, in this video we're going to look at the normal approximation. So on your journey so far you should have looked at binomial distribution. So what you're looking at here is a picture of a binomial distribution. If you have your graphical calculator, you may have seen this picture very often. Now for example, let's say this is number 12. So it could be shoe size of people. There's a pretty big feet coming down this way. But the most popular size was a 12. Maybe it's children, who knows. So then if it's children, I think there's a 13. So let's just make it a bit easier. There's 1. Oh, let's just make it easier. 13, 14, 15, 16. Right, so these are the amount of people that had this shoe size. Maybe they're NBA players, who knows. So there's nothing that exists in between those lines because it's discrete value. You can't have we technically can have 12.5, but you can't have a 12.4, you can't have an 11.783 shoe size. There is nothing there. What I'm about to show you is a piece of software that is going to just make the bars a little bit wider to fill the space. So it's going to actually look a little bit more like this. But what I need you to keep in the back of your mind is it's the middle of those bars is the actual result. We're filling the space. What also is going to happen is they're going to draw a normal distribution curve. And you'll see that this one looks very symmetrical, doesn't it? And if you were to draw a curve that hits the center of all of them, it looks something like that. You could say it looks like a normal distribution curve. But on a curve that I've drawn in green, that's continuous. There's an infinite amount of numbers along that x-axis. You can have your 11.783 because it's not a discrete value. It could be the length of the foot, for example. But what you're going to see is discrete, these black lines, with these boxes around them to fill the space with the red bits. So let's go ahead and have a look at this. Yes, I would agree. Let's just make this all a bit bigger so we can see it. Right. So unfortunately, I've just missed off this top part, which tells you how many our sample size is. So we have n to be 20 here. You're just going to have to take my word for it. Now, n is 20, and you can see the p being 0.3, for example. Just remember what I said. You're actually looking at the center of the bars. And if I put a normal curve on, you can see it is definitely not in the center here, it's off here. The heights of these bars, they're not looking particularly symmetrical like they were when I just drew it. If we make n small, it gets worse. If we make the probability smaller, even worse. It doesn't even look like a symmetrical curve at all. But something strange happens when you make n 50 and you make the probability close or exactly a half. You can see that symmetry starts to appear. It looks like it's starting to take the shape of a normal distribution. So mathematicians are curious, how accurate is it if we treat it as a normal? How can we take something that's binomial and change it into a normal distribution, which is continuous, because it looks like it should be. And that's what this lesson is all about. But from this software, I want you to take that when n is 50, you can't see it, but I'm telling you n is 50, and the probability is close to 0.5, it looks like a normal distribution curve, or it fits under that curve. You can see if I take the probability away, it starts to get less symmetrical, but still pretty good. Right, let's go back to where we just were. Here we go. Now, new slide. Here we go. Now, the course, they want you to learn this bit here. This happens so you can use what's called a normal approximation, so we can use the normal curve to represent something that's binomial when n is large, p is close to 0.5. That's so ambiguous. So what is large? Is 50 large? Is 100 large? Is 1,000 large? Is 30 large? Who knows what that means, but that's what they want you to write. And the probability is close to 0.5. Well, is 0.6 close to 0.5? I think it is. Maybe it's not. Is 0.54 close enough? It's too ambiguous. So we always used to use this language, which is, n times p. If that's greater than 5, it's suitable, but that and n1 minus p, or q if you prefer, has also got to be greater than 5. So if it meets both of those, it's a lot clearer, but that's not on your spec, but it's used, right? So you can write it because it is correct. But if you just want to tick all the boxes, it's actually what I've circled in green. So let's start looking at this and where it gets a bit tricky. But it is important to understand you are taking a discrete value, you're not turning it into a continuous value. That is impossible. It's just represented as a continuous variable because it matches, it looks very symmetrical, and it's only in those special conditions that we can do it. Now, if I asked you to say, on average, how many heads would you expect from 200 coin tosses? You'd say 100, right? Because what you've just done is you've done 200 times the probability of it happening. So you took how many samples and you times it by the probability. Very easy to remember that the mean is just that, the number of samples times the probability. What's a bit harder to remember is the standard deviation. So to get your variance, it's NPQ, or NP1 minus P, and then to get your standard deviation, you're going to have to square it. So there's two things you have to remember. That's the first thing. Now, so let's have a little play with this one. Is n large? I don't really think so. Is 0.4 close to 0.5? No, but NP is greater than 5, and NQ is also, that's 18, is also greater than 5. So it is suitable to use. You can see that's a little bit clearer. In their exams, they will make it 300, and they will make it 0.48, for example. So it will be pretty obvious. So we need to try and, oh, I've got a slight error there, that should be B. Sorry about that. So we've got a binomial distribution here. We're going to assume it can be represented as a norm. But before we do that, we have to change the parameters. So we're going to say it's distributed normally. X can't be binomial and normally distributed. It can't be discrete and continuous. So we're going to change that to a Y. Now, we need to find the mean, so that's going to be 12. NP, remember, I'll write that down. So this is NP. And we also need to work out our new variance. So it's NPQ is our variance. So let's go and write that one out now. So we've got 12 times 0.6. So that's our variance. Don't really want that. I want the standard deviation. And I make that 2.68. I'm going to just leave it to there. That should be enough. So that's my NP1 minus P, or NPQ is my variance. I've square rooted it to get it in that form that my calculator is going to run. Remember, when I'm typing these in, I can use that whole answer using my answer button. Right, so what we have is this picture now. We have our Y, remember, let's say Y, so we have to change the variable. We know the mean should be 12, and we are looking at this 10. But now we have a problem. Discrete values do not fit under a curve. We have to bulk out those spaces. So this line, this 12, remember, is our first question here. It's the probability, whatever this discrete value is, let's say it's a number of bottles, for example, is less than 10. Might be the number of Pinot Grigio sold that week is less than 10. But this 10 here, you can't have 10.4, you can't have 9.8. So we're going to have to fill the space. Remember, this bar would be 1 centimeter because there would be an 11, there would be a 12, there would be a 13. So that single red line is actually that big purple box of going down from 9.5 to 10.5. And we want to know everything less. So we don't actually want the red line. So if we don't want the red line, we don't want the purple box because they are one and the same. So we can say that this one is approximately equal to the probability of Y, our continuous variable, less than 9.5. I'm not going to go ahead and work it out. It's just teaching you this strategy. And what these are called These are called continuity corrections. Continuity corrections. This is the bit that everyone forgets to do. They just put 10 in and they think it's fine. But you have to remember you're taking something discrete, filling the gaps under a continuous curve. Now, it's worth mentioning while we're here, if it was now less than or equal to 10, we would want to take up to that red line. But because that red line is represented by this big purple box, you have to take the whole box because they are one and the same. So essentially, if you enter the box, you take the whole box. Let's look at this next one. So I'll draw another picture here. We know the mean is 12. We want more than 14. But this 14, this discrete value, doesn't exist as a single point. You're going to have to fill up the gaps. So we want more than 14, so here we are. So this is approximately equal to the probability of y being greater than 14.5. If we change the question to include the 14, we want to include the red number, because we have to include the whole box. Sorry. Oh, I didn't actually change that last one, did I? So now it's not just doing that. It would be y is greater than 13.5. And on this last one, sorry about that, I've got too distracted with writing continuity fractions. And now, because we take the box, it would now be up to and including 10.5. Okay, so we have to change these numbers here, are highlight. This is your continuity correction, whether you take this one or this one, and it's all to do with this sign, whether it includes the box or doesn't include the box. You'll notice I didn't actually bother, but I could do this, because we don't really pay much attention to those signs when it's continuous. You hopefully had that understanding from the previous video. So on this one, when there's 2, we've got 12, 11, we've got 14. I'm going to just draw a box around them just to remember we're filling that space. This is utterly crucial. Let's label our axes. You can see it's an X there, but it's a Y because this is our continuous picture using to solve a discrete problem. We want it more than or equal to 11, so we definitely want this bit here. Oh, that should have happened. So we definitely want this bit here. Do we want to go inside the box? Yes, we do. So we want to take the whole box. So we want the 11 included. But we don't want to go up to the 14 line, so we don't go in the box. So this is approximately equal to this value here, which is 10.5. That's a y. Up to 13.5. So that's the bit you could type into calculator. I haven't written this one down, but it's just come to me. What about if it was, say, this? If it was just 9, then you're in this situation again, 12, and there's 9. And you would take that whole box then, so you go from 8.5 to 9.5. Let's look at an actual question. No, I don't really like that one. So let's look at this one. So pause the video, take it in if you need to. And when you're ready, just hit play. Right, so they haven't defined a random variable, so I'm going to always go for x. And we're looking at the number of yellow flowers. So number of yellow flowers. And x is distributed binomially. We have 80 flowers, and we know the probability of it being yellow is 0.55. Okay. So this is about percentage error compared to a normal approximation and an exact, normal and a binomial for exactly 50 flowers. Okay, so let's I'm going to put big B for binomial over here, put big N over here for the normal distribution. So for this one, x equals 50. That's the question. The probability the number of yellow flowers is exactly 50. So you can type this into your calculator. If you want to be really proper, if we have 80 flowers, we're going to choose 50 of them to be yellow. The probability of success is 0.55. We want that to happen 50 times, and the probability of being unsuccessful is 0.45, and we need that to happen 30 times. But you don't type any of that into your calculator, you just use your binomial distribution. Just change your tail to be equals and put in your numbers, so 50, number of trials 80, 0.55. That's probability of success. You get a picture with one vertical line highlighting the bit we're looking at, 50, and you should have this answer. And I'm going to write it down to a relatively decent amount of accuracy, because I can't get that number. Right, so the normal distribution. So I'm just going to go ahead and say y is distributed normally. I now need to calculate the mean. So that's, if you remember, NP, so 80 times 0.55, so I get 44. If I times that by Q, which is 0.45, I get my new variance. Don't really want it in that form, so I'm going to square root it, and I get 4.4497. And I can take that number and put it into my calculator. Right, so we are here. We know the mean is 44. Label your axes. There's 50. 50 is represented by a stretched out bar to fill the gaps, and we need to know the probability of x equaling 50. Using our continuous model, our normal approximation, that is the same. Remember, just like I rushed in that last slide, you can do an equals distribution. You're just taking the box. So that's 49.5 to 50.5. So this time I am going to type this into my calculator. So normal distribution, make sure you've got both tails being included. Your lower 49.5, upper 50.5, the mean to be 44, and I'm going to use my answer button to put in the full extent of that standard deviation. And I make that to be approximately to 0.03618. I'm going to leave it there. Okay. So we're nearly finished. It says percentage error. So percentage error is the difference. And you always want to make that positive. So have a look which number is bigger. This one here is bigger. The actual binomial, the exact answer. So we're going to start with that one, take away this one, and then you're going to divide it by what it actually is, which is the binomial. So here we go. So if we type these in, 0.036518, hopefully I've typed that in correctly, minus 0.03618, I make my error to be 0.00338, and it should be this one, 0.0366518. So I'm going to head and divide that by 0.03518. And obviously percentage is times 100, so let's squeeze this in, times 100. So the error is only 0.926%. So you can see how accurate this normal approximation is compared to the exact answer. So that's only 0.9%. So that brings us to the end of this video. Please leave any comments. I hope it's helped you, and best of luck with the questions.